So it's nice to already have heard a lot about unsatisfiable cores, about correction sets, because this will come back in this presentation. So what I'm presenting you is joint work with Thias Guns and well, a student of us, Emilio. Oh, this is progressing by itself. And actually, it's an ongoing project. We quite recently started it. So it's a relatively young research project, and it's about generating explanations in the context of CSPs. There are still lots of open questions, as you can expect, and some history. This actually, sorry. This actually originates this research from the previous Holy Grail challenge, which is a nice connection. Nice to be here now this year as well. And so this work is our take on explainable AI. What we want to do is, well, instead of trying to explain things that are hard to explain, let's start with the easy things, say. And by easy, I mean, in the context of constraint programming, we have this nice model, we have this nice theory that specifies what good solutions are. So let's see what kind of explanations we can get out of that. So we will exploit this rich structure we have to provide explanations, and the goal is that they should be human understandable. Of course, what exactly that means is it's hard to define, but what I mean by that is that we will not try to explain what the solver does in a way that can be machine verified, but we will try to explain the easiest way to obtain something. Even if that's not the way that the actual solver obtained it, we will search, and this will be a computational problem then, we will search for an easy way to explain certain derivations a solver makes. And one place where that might be of use is in the context of interactive constraint solving. Suppose you're tackling a problem interactively, for instance, a scheduling problem, and there's a solver helping you, and now and then he makes derivations, and suddenly he says, okay, you're trying to schedule that there. Well, this will no longer be possible, and you're surprised, and you want an explanation. Why is this? And then this explanation can be in terms of the constraints in the background. So yeah, in last year's Holy Grail challenge, there was the challenge was, well, we all know logic grid puzzles, this kind of Einstein puzzles or zebra puzzles, they're also called, in which you get a riddle in natural language. And the challenge consisted of 3 main parts, I would say. Take such a riddle in natural language and translate it into a CSP automatically, preferably. Solve this CSP and explain in, I think it was specified in natural language, but at least in a human understandable way, how a human could have solved this puzzle. So we tackled this challenge partly thanks to a master's student who already did the first part the year before in his thesis. So that was an easy thing to start with for us. And our focus has mainly been on the third part, on how to explain this in a human understandable way, how to solve such puzzles. And recently we got a paper about this at Akai. And what I will present now is the work in this Akai paper, but also some follow-up research. We've got a journal version under review now, and a follow-up conference paper. So I will talk about some unpublished stuff as well. So to give you an idea of where we are now in this explanation generation project. So what you can find in the Akai paper is a formalization of the kind of explanations we want to get, and we call them stepwise explanations. The idea is we've got some derivation that the solver can make. Possibly he made it by doing search and saying, well, now this is the only possibility. Possibly he did it by some form of consistency, by some propagation method. How he obtained it is not really our concern. But what we want to get from it is a sequence of steps, simple steps. And simple will be, well, defined by some objective function measuring how difficult a step is. Preferably that objective function would serve to be close to what humans perceive as simple, but we're not there. So we're not pretending that we have some method to know what a human will find simple or anything. Maybe this can be learned by experiments with humans or something. Our focus is now mostly on the algorithmic aspect. And what we then had is an algorithm that that solves this stepwise explanation problems by reducing it to finding unsatisfiable cores. And we also had some heuristics to search more efficiently for this kind of explanations to help our algorithm. And we had some experiments. And what I had on top of that now in the current presentation is a notion of nested explanations. This is a conceptual extension where the idea is to explain on 2 different levels of abstraction, or possibly even more than 2. And what I will also talk a little bit about is incremental algorithms for searching unsatisfiable cores. But I'll come to that later. I will first focus on the basic idea. So a logic grid puzzle, just a brief reminder, there's a set of clues in natural language, and there's a set of entities. There are a couple of sets of entities that need to be linked. And each entity is linked to exactly one entity of each other type. For instance, each person has a pet, has a color of a house, has a house number, and so on. And this kind of constraints I will refer to as bijectivity. And also the links are consistent. So if my pet is a dog and the dog lives in the yellow house, then I live in the yellow house. This kind of constraints I will call transitivity constraints. And so what we did was we had already this automatic parsing of this kind of the typical clues that occur in such puzzles, and they give us a constraint representation. And important here in our work is that this constraint representation, it's actually not so good. If you go look at it, you will probably easily see, oh, well, you could write this much better so that it has better propagation properties. But that's not our focus. I think that if you rewrite this constraint, all these constraints with a focus on being explainable, then you could get something that propagates very well and in which a very weak propagation mechanism could probably already bring you very far in the explanations. But we don't do that. So we just say, let's take the constraints for granted as the natural language tools gave them to us, and let's work with that. And use them as a black box, basically. All we know is that we have some constraint representing a certain natural language sentence. We also did no modifications to the solver. So we didn't extend certain propagators with explanation mechanisms. What solver can do is solve constraint satisfaction problems and also give us unsatisfiable cores. And in the ideal case, as we will see, we will not just get any unsatisfiable core, but we will get specific types of unsatisfiable cores, but we come to that later. And I'll just demonstrate the system a bit so that you have an idea. You can also try this out online. So what we have here on the right is a set of clues. For instance, the person who ordered capellini paid less than the person who chose arrabbiata sauce, and so on. And what we have on the left is a grid that's typically used for solving such puzzles, in which you can put checkboxes if you know that a certain entity is linked to a certain other entity, or a minus if they're not linked. And the explanations then take the form, they highlight a clue. Well, for instance, this first clue, the person who ordered capellini paid less than the person who chose arrabbiata sauce. In itself, it can be used to derive that arrabbiata sauce didn't have the cheapest price, or didn't cost 4. And in the beginning, the explanations are quite simple. There's just a clue that's used to derive some certain facts. After a while, if you click through it, you get more complex explanations, such as here, a bijectivity constraint is used, saying, well, if this blue square holds, if arrabbiata sauce was linked to farfalle, well, then arrabbiata sauce was not linked to capellini or tagliolini or rotini, and so on. And in the next step, you see a transitivity constraint being used, saying, well, if arrabbiata sauce was linked to farfalle, and Claudia did not order arrabbiata sauce, well, in that case, Claudia did not order farfalle. And so what we do at each step is try to find a simple possible explanation for some literal to be derived. And this goes on and on. And actually, the puzzle I'm showing you here is quite an interesting puzzle, because it was sent to us by someone who knew that the student had done this work on this type of puzzles, and who wondered, well, this puzzle, is it actually correct? Because he didn't manage to solve it. And so then we produced his explanation, and then he was convinced, yeah, it's indeed correct. It has a unique solution. So he was happy afterwards. So you can try to solve it yourself, and if you're stuck, you can always ask our Zebra to help you with it. So that's the general idea, and so you'll see that there are more complex explanation steps coming later. So yeah, just a small warning for the rest of the talk. I'm used to using the logic terminology more than the constraint programming terminology. So in particular, I might use the word model to refer to what you would call a satisfying assignment, and I might use the word theory to what you might call model. So if you hear a strange use of model, then that's why it is. I will typically use the logic terminology more. And in our paper, we also formalized everything in the context of propositional logic, but in fact, the ideas are quite generic in the sense that they don't really depend on what the language of your you write your constraints in exactly is. So this is our definition of an explanation. So what we're looking for is we're given a theory, aka a model in constraint programming terminology, and we're given a certain interpretation. And we know that from this theory and this certain interpretation, some other interpretation follows. We're looking for a subset of the theory, and this subset here is called S. We're looking for a subset of the current interpretation, so some parts of it that are relevant, and they should be enough to explain some newly derived literals. So everything that's in the new interpretation, but not in the old one. So this is very similar to what was said in the first talk. And we're not just looking for any, but we're looking for non-redundant explanations, because you can always say, well, the entire theory and the entire current interpretation, well, together they explain whatever we can derive from them, and we're done. But we don't want to do that, of course. We want to get a small explanation. And this is called a non-redundant one here. And well, some important correspondence here is that what we called non-redundant explanations, they correspond one-to-one to minimal unsatisfiable cores, also sometimes called minimal unsatisfiable subsets of a different theory. So if we want to explain how a certain literal follows from an assignment plus a theory, we can also ask for an unsatisfiable core of this assignment, union this theory, union the negation of the literal we want to derive. So these correspond nicely one-to-one, which allows us to reuse existing unsatisfiable core algorithms. And so we will, on top of searching for non-redundant explanations, we will assume that there's some kind of cost function that quantifies how good a certain explanation step is, and we're looking for cheap ones. For instance, in the case of our logic grid puzzles, just using a single bijectivity constraint, it's very easy. So we will give that kind of explanations a very low cost, while explanations that combine 3 different clues, figuring out what's going on there is not easy, and so we will give them a very high cost. Combining 2 bijectivity constraints is often also still a lot easier than combining 2 natural language clues, because there's a structure in this bijectivity that always comes back. So yeah, we just assume that there exists some cost function that we will, and we will use that. And then what we're searching for is for a sequence of steps, explanation steps. You start from, say, an empty interpretation in which nothing is true yet, or some interpretation, and you want to end up with this one on the right. And then there should be a sequence of steps that's as simple as possible and that reaches the final conclusion here. And in our case, the final conclusion would be the solution to the puzzle. So what we did in the Akai paper was we developed a greedy algorithm in the sense that it just starts and it searches the simplest next step, and then it will explain that step, and it keeps on doing this greedily under the assumption that we want to minimize the hardest step in the explanation. This would be correct, but it doesn't. If you want to do some other aggregate over the sequence, this would not necessarily be correct. the way our algorithm works is, well, at each step, we will just go over all literals in the solution, and we will search unsatisfiable core or unsatisfiable subset that explains that literal, and we will pick the cheapest one. And then there's some caching of results in the meanwhile. Yeah, our solution builds on the IDP system, which is similar to the system from the first talk. It's a lazy clause generation solver. Its input language is first order logic, but in the context of a finite domain. And there's a set solver underneath. Yeah, and there's a with this here we find the minimal unsatisfiable subset. There's some remarks there. In practice, a single call didn't suffice because so it only had a minimal unsatisfiable subset, not cost optimal or something built in. So in practice, there are lots of minimal unsatisfiable subsets that turn out to be very bad explanations because they might be minimal, but they might be using a lot of constraints and everything entailed by them instead of simply using some stuff that's already in the assignment. So in practice, a single call didn't suffice. And there is because of this limitation, we had to prune some certain results based on an approximation of the cost. And especially, we didn't have a guarantee of optimality, and it was terribly inefficient. So these are some negative results about our Akai paper that we're now trying to solve. And I will just show you what how we explain a single step in an algorithm. This is actually what we wanted to write in the Akai paper, but we couldn't do it. The reason is, so what this does is we loop over all literals in the solution. And for each of these literals, we find an optimal minimal unsatisfiable subset with respect to f. That was our goal. But of course, there was no mechanism to find such an optimal minimal unsatisfiable subset, only for a minimal unsatisfiable subset. And so we had to work around this. Yeah, this was replaced by several calls to minimal unsatisfiable subsets with increasing sets of constraints. And then we will just pick the best one. That was basically it. We pick, of all the literals, we pick the best explanation, and that's the one we're going to explain next. And then we come in the next step of the explanation process. So we developed this visual explanation interface. We had this cost function that I explained already, that a single, like this bijectivity axiom, is very cheap, but using multiple constraints is very expensive. And yeah, there's one small remark here that often our constraints have terrible properties. I already mentioned this in the beginning as well. So they really don't propagate well by themselves. For instance, this constraint in natural language, the person who ordered Capellini is either Damon or Claudia. It was translated automatically into this first order sentence. There is a person who ordered Capellini and who is either Damon or Claudia. But this one will not, this constraint in itself doesn't entail that one of the other persons didn't order Capellini. So we need to use this one in combination with the bijectivity constraint in order to actually get something out of it. So in a certain sense, by using this type of bad constraints, as I would call them, we get some more tolerance towards people using bad models, but still expecting good explanations. So where could this be used? Before I go to our very recent work, where could this be used? Well, one way to use it would be to teach humans how to solve a certain problem. So if they're stuck and they want to know what kind of reasoning mechanisms are used, they can say, okay, how would you solve this now? For instance, what we saw on this is that in certain puzzles, we saw patterns occurring in which the solver decided that the next simple thing to do was to combine 2 or 3 bijectivity constraints. And actually, it's always looked the same visually. And this was a mechanism that you could often use in the use to solve this kind of puzzles yourself. So the idea there was that if there are you could see that there were rows that had no more possibilities. Yeah, I should have prepared this to show it to you because it's very hard to explain it, but that if you combined 2 rows with different types of entities, that there was no more possibility to be matched. But yeah, okay. So we could also use it to quantify problem difficulty. Namely, for instance, in this type of logic grid puzzles, what's the most difficult step you have to find in order to solve the puzzle? With some puzzles, it will be very easy. And so if we have a good measure, a good cost of an explanation step, then we can search for the cheapest way to find it. And this way we could quantify how difficult a problem is. And it could be used in the context of interactive configuration, and interactive planning, interactive scheduling, to explain why certain things are no longer possible or must happen, and so on. And then the next step we took was, we saw that certain explanations generated, especially for the difficult puzzles, were still quite hard. And if we looked at them, after a while, we could see, well, yeah, this is what's actually going on here. And if we then wanted to explain, we noticed it when doing demos, if we then want to explain to someone why this explanation that the solver produces is actually a valid one, we would always do this by some form of counterfactual reasoning. We would say, well, suppose that the derived thing is not true. Then you can see this and this and this and this. And so we decided, well, if we explain it that way, yeah, maybe we should also build it into the system. So if we go back to the demo, what you can see here is, here's a difficult explanation step happening. It says, well, if the clue, the person who ordered tagliolini paid less than the person who chose marinara sauce, in combination with these three facts, that tagliolini didn't cost 4 and Angie didn't order 12 or 16, didn't pay 12 or 16, we can conclude that Angie didn't order marinara sauce. If you don't understand this, you can say help, and I don't understand this derivation, and then he will, towards contradiction, assume that it's not true and show you how only using these things that he promised you to use, you can get to a contradiction. So in this nested explanation, it has now been broken up in smaller steps how to get to a contradiction. This is actually some form of search, you could say. We make one choice and then we see that we will get to a failure. You could nest this possibly multiple levels if you wanted. And then the other extension, which is one we're working on very much now, is to build algorithms that actually compute an optimal unsatisfiable core or an optimal unsatisfiable subset with respect to a certain optimization function. And the algorithms we're developing are based on the hitting set duality, which is famous from Maxat solving, but also cardinality minimal unsatisfiable cores have been generated with this kind of algorithms. And especially we're doing, on top of the existing hitting set based algorithms, we're doing two things. One is we're making our unsatisfiable core computations incremental, because we know that we're generating an explanation. We know that there will be multiple calls to an unsatisfiable core solver. So we want to reuse as many of the results of the internal data structure that have been computed as possible in the next call, to make calls towards the end more efficient. And the other one is something we call constraint OMUS computation, so constraint optimal unsatisfiable cores or unsatisfiable subsets. By that we mean is that we want to allow the user who wants an unsatisfiable core to be able to write constraints about what it can look like. For instance, and the main reason we're doing that is because of this loop here. This loop goes over all literals, and for each literal, it computes an unsatisfiable core. But we want to get rid of this loop. We would like to phrase it in a single call. Namely, we would like to ask a solver, give us an unsatisfiable core that contains exactly one literal. And then of a bigger theory that contains all these negated literals, but there can only be one of them in there. So that would be the one to be explained. So we want to write constraints about what our unsatisfiable subsets would look like. So these are type of meta constraints. Yeah, we don't have experiments yet there because we're still implementing everything. But that's the direction we're going now, trying to make this process efficient. And there's more future work in the pipeline. For instance, as I mentioned already, we would like to, at a certain point, learn the optimization function, namely by doing experiments with humans, figure out what do they find an easy to understand explanation, or at which level of abstraction would they like to see an explanation. We would also like to explain not just derivations, but different type of why queries. So why is this the optimal solution? Why does this specific thing hold in all optimal solutions? Maybe. Yeah, we want to scale up. We want to be able to tackle more problems of a more realistic scale. And yeah, all these algorithms, we want to make them incremental because we expect that this explanation queries will not just be a single one for a single problem. There's typically going to be many of them, we expect. So with that, I would like to thank you. And if there are any questions, I'd be happy to answer them.